Dear friends, dear colleagues, good morning. It's a pleasure to be with you today. In these 30 minutes, I'm going to talk on how to securely share health data. So, thanks to the COVID-19 crisis, I think by now everyone has understood that health data management doesn't work properly and that it needs vigorous improvements. Now, this improvement actually is absolutely doable with appropriate tools and processes. Right? Considering the time span over which these data have to be protected and how much is at stake, clearly these tools have to be based on mathematically proven protection techniques. Once we achieve this, this will give data management the robustness and efficiency that it needs and deserves. And it is my belief that the security and privacy research community must and can help, and we're going to see why. Let me start with an example, which is an example of a medical question. How effective is hydroxychloroquine to treat patients affected by COVID-19? As probably all of you know, this medicament has been used for many years to treat other diseases. And the question is, does it make sense? Is it desirable to repurpose it for COVID-19, considering, taking into account the fact that it can have, in some cases, severe side effects? So at the beginning of the pandemic, it was a very lively controversy. It was unclear whether this was appropriate or not. And then a paper seemed to bring a conclusion to this debate, a paper that appeared in the Lancet, one of the most prestigious medical journals. And what the authors have claimed to have done in this case is to have taken the data from 96,000 patients in hundreds of hospitals in all the continents, and as usually done, separated them between, let's say, treatment group and control group, and then compare the mortality to see whether the treatment was bringing some substantial improvement. Right? The conclusion of the paper is that, unfortunately, there was no improvement. So in terms of, let's say, in terms of for the patients who had received this treatment, and unfortunately, there was an increase in the well-known negative side effects in a number of patients. As a consequence of this paper, many COVID-19 trials related to hydroxychloroquine were stopped internationally. We'll come back to this paper in a few slides. This is not the end of the story. Now, before doing that, let me say a few words about multi-site studies. The benefit of such studies is quite obvious, right? It increases the amount of available data and thus the statistical significance of the findings. Unfortunately, it also comes with a number of challenges, right? Notably, the need to interface several ethics committees to obtain approval and deal with the IT services of the various hospitals involved. In the case of international studies, the diversity of legislation can also be an issue. And there is, let's say, a daunting problem related to the heterogeneity of data semantics and of data quality. Right? And everyone working in this field will tell you that this is a really major issue, probably the most significant roadblock. At the same time, there is reluctance to share data, right? Because transferring data means losing control and losing publication advantage. So this heterogeneity actually is actually partially, at least, the consequence of this reluctance, right? And we will see that if we can overcome this by finding a way to share the data without transferring the data, then this is a very significant step in the appropriate direction. Let me also mention that there is a widespread practice in medical studies that consists in de-identifying the data. So the research is usually that, let's say, the research usage of de-identified data requires normally a patient consent, whereas if the data is anonymous, this is not the case. Overall, there is little awareness of crypto and of techniques such as differential privacy in the biomed community. So if we push a bit further on this notion of multi-site studies, the classic approach is to go fully centralized, meaning that the various sites transfer their data to a trusted third party who runs the algorithm and then comes to the conclusions. Now, for the reasons mentioned before, this is something that is not necessarily desirable for these institutions providing the data. So another solution is to go for a more something that we can call the meta-analysis approach, in which each of the institutions provide not the raw data, but rather the aggregated data, unencrypted. And so then the third party becomes semi-trusted and runs the algorithm. And if this is still not enough in terms of protection then, or decentralization, then another solution is to go to something that is fully decentralized, where the algorithm is sent to the data are not moved at all. There is computation of the partial result, and then the partial result is sent from one side to the next, unencrypted, and then at some place a final computation is made. Now let's look a bit more into this notion of send the algorithm to the data, which is very appealing and is probably actually the way to go for the future. So instinctively or implicitly, people like to believe that the data look like this. There are many patients and there are few attributes or few covariates per patient. The algorithm arrives or shows up, computation is made, and then the output is actually the outcome of the local computation, right? And the hope is that the there is some data protection that comes from the fact that the output leaks nothing, right? Because the aggregation will essentially conceal the individual data and will in particular prevent re-identification attacks. Are we sure of this? That's not obvious, right? If instead of having this situation, we have something of this kind, right? Where there's many attributes and few patients, right? Which is going to be more and more the case, because the more progress is made by medicine, the more data is going to become available per patient. And if there is stratification, likewise, right? The number of patients per institution is going to be small. And of course, in the case of genetic data, the situation is even worse, right? In this case, it does not make sense to rely on aggregation to obtain actually privacy protection. So let me mention something about the ethics committees. So ethics committees play an important role. They take as an input a study protocol and a consent form, and then take into account the legislation, some ethics considerations, and so on, they produce a go no go decision for the study, for the proposed study protocol, and a feedback, right? But this is a very slow and manpower hungry and tedious process. And it requires to obtain informed consent, and there's a diversity of consent forms, so it's complicated. And the ethics committees make an on-paper a priori evaluation. And usually they have relatively little control on what happens afterwards. And finally, there is a risk of race to the bottom, in the sense that those of the researchers that manage to obtain permissions to see more data will extract more value and will have a competitive advantage in terms of publication. So to come back to the paper I was mentioning previously, it was retracted, right? And this was quite a big shock in the community. The paper was published on May 22nd, retracted on June the 5th, because researchers, other researchers asked the journal questions about the data and how the data had been collected and so on. And it appeared that the process had been so, let's say, unprofessional that the journal had no other option than retracting the journal, the paper. Right? And as you can imagine, in today's situation where the trustworthiness of scientists is more and more questioned by some politicians, this is a very, very unfortunate event. And actually, a similar story happened with another prestigious journal, the NEJM. Now, considering all this, it is our firm belief that what is needed here is a technology disruption, in the same way as it happened for locomotives that at some point switch from the steam engine to the electrical engine that is safer, cleaner, easier to operate and to maintain, more reliable. We need a switch of the same magnitude for the sharing of health data, right? So we need this technology disruption. So I've described the current situation in terms of questionable data protection guarantees and so on. The future is, if you think about it, essentially making use of the right crypto. And this, based on many years of reflection and discussing with the specialists of the field, etc., has to be a combination of secure multi-party computation and homomorphic encryption. They have to be taken in combination, and so we'll call multi-party homomorphic encryption the combination of the two. Combining those two is not a new idea. This acronym is a somewhat new idea, but the idea itself of combining these two techniques is more than 10 years old. And with this, the consequence, the benefits will be to streamline the approval processes, to provide mathematically proven guarantees, and to move towards really decentralized trust, and as a consequence to federated learning. Homomorphic encryption, so probably most of you already know what this is. It means essentially computing on data without seeing them. So if assume here there is a computation to be carried out on input XA from Alice and XB from Bob, none of them is willing the other one to see this input. So this computation will be carried out in the following way. So in this case, Alice will encrypt her own value. She will send this value encrypted to Bob. Bob will evaluate the function without having access to the clear text of what Alice has provided, and will the encrypted result back that Alice will be able to decrypt. And Bob will be able to decrypt this result as well. Right? So there's been a lot of work on this topic. Here are two examples of how to achieve this in practice with either, so in 2012, there was already a good solution to do this on integer vectors, and then in 2016 on float and complex vectors. Now the question is, what if there are more than two parties? So in that case, what is needed is actually to bring secure multi-party computation, and as mentioned, as combined with homomorphic encryption, this leads to multi-party homomorphic encryption. So the idea here is that given a homomorphic encryption scheme, to distribute this secret key securely, and then to perform secret key operations that become de facto multi-party protocols, right? So I'm simplifying things a little bit here, but just to give you the intuition for those of you who are not necessarily too familiar with this topic, right? So there's here the generation, there is a protocol to generate the public key, and then the decryption is actually carried out as a collaboration of the different parties involved, right? And the decryption can be either, can require an involvement of all the parties, or if this is considered to be asking for too much, then it can be a threshold. Then it has to be, it can be just T out of N parties that are actually needed for the decryption. Or another approach is also to make use of, let's say, to not rely on a common public key. And this is another, let's say, another possibility, right? There are many variants, let's say, around these ideas. So now, if this is done in combination, then it is possible to achieve high performance, secure N-party computation, right? So the idea here is that the N parties want to compute a function f over their joint input in such a way that only the output is revealed. So they don't see the other partners or their parties' inputs, right? So this is shown in this, let's say, figure. And so there have been, let's say, contributions that show how to achieve this on ring learning with errors, so RLWE. There is something that relies on lattice-based crypto, as some of the proposals that I've mentioned previously. I spare you the details because it would take too much time to dive into this. But let's say the important thing is to understand what this provides and how it actually responds to the challenge that we are addressing here. Now let me introduce the notion of cohort exploration. So what is a cohort exploration? So a cohort, first of all, is, as you probably know, a group of people that is part of a clinical trial and actually is observed more often than not over a period of time, right? And so the first thing to be done after the approval has been obtained from the ethics committee is to perform a cohort exploration, meaning discovering how much is available, how many patients respond to or are, let's say, have data that are of interest with respect to the research question that is addressed. And this is typically done by Boolean and an OR operator. So it's relatively simple technically, but it's very important to have this. Once it is achieved, the next step is the analysis. And so this is typically operations that are of statistical or machine learning queries on a set, in our case, a set of distributed databases. And of course, it has to be done while protecting individuals' privacy, right? And so the operations are typically statistics operations or machine learning operations. So the researcher sends the list of covariates or attributes and the ML model, and will receive as a response the trained ML model. Right? So now let me mention one thing here that probably many of you who are familiar with the topic of machine learning already know, is gradient descent, right? So I'm taking here a toy example. Assume we want to find the linear regression for these 6 dots, so the line that best fits these 6 dots. If all data is available in a single place in clear text, it's very simple, right, to perform either linear or logistic regression by making use of gradient descent, right? And this is depicted here on this figure. I'm simplifying things a little bit here, but still. And the outcome will be that we find the line that best approximates those. Now, the question is, how do we achieve this if the data is not available centrally in clear text, but on the contrary is available in different places and you cannot have access? How do you deal with this? Right? So the gradient descent actually can be extended to this, and it's important also to take into account that actually it can go beyond a linear or logistic regression. It can also be a solution for generalized linear models and for neural networks, right? So, and actually a GLM can be represented as a kind of degenerated simple neural network as depicted on this figure. Right? So what is needed to solve all these problems is a distributed gradient descent, right? Now, assume we have 3 data providers. Each of them has access only to its own data. So in this case, again, it's a toy example. So let's take the 6 dots that we have seen before. Assume DP1 has the first 2 dots. The DP2 has has dot 3 and 4, and DP3 has dots 5 and 6. Right? Now, as you can see, if they just use those local data, they are going to come up with conclusions that are highly contradictory with each other, right? Because they don't have all the dots, right? So how are we going to avoid this? Well, the solution is intuitively relatively simple. The idea is to emulate actually the situation, the centralized computation, by making use of a decentralized, let's say, algorithm in which, so first of all, the querier is going to define the query, right? For example, training of a linear regression model on specific attributes or a neural network. And then each of them is going to actually train the local model on its own data, right? And they will iterate on this, right? They will collectively iterate to combine their encrypted local model. It is encrypted, but as we make use of homomorphic encryption, we are still able to make computations on these encrypted values. And so after a certain number of iterations, the system will be able to provide a model that is the result of this collective training, and that is actually, depending on how the system is configured, is either, so the model is either kept secret for oblivious predictions, if you wish, or revealed to the querier. Right. So we have implemented a system of this kind, and here you see some the outcome of some of the benchmarks. So this is a case of logistic regression. This is on 2 databases. The first 2 are medical. The third one is a well-known database of handwritten digits. And as you can see here, what is shown is the accuracy in terms of the centralized, how good it is when you have all the data available. If you do an independent training, just each of them without aggregating their results, distributed not secure, and meta-analysis, which means distributed secure. And what we see here is that actually green, so the proposed solution is actually, in terms of accuracy, there is no loss of accuracy with respect to the distributed not secure or to the centralized. Now, in terms of, we applied this also to neural networks. And as you can see in this case, it's a slightly different set of databases. But as you can see in this case, there is already a small decay between, by decentralizing, because it's more complicated. And we are still working on trying to make yellow as close as possible to blue in terms of accuracy. So the distributed not secure as close as possible to the centralized, and the green, which is actually the secured version, called Poseidon, which is say the ML, let's say the neural network enabled version of Medco to make it as close as possible to the yellow one. So we're still working on this, but as you can see, the difference is not very important. In terms of performance, what is shown here is that thanks to the combination of these two crypto techniques, the good news is that actually with reasonable data sets, the response time by running this on off-the-shelf hardware, the response time is in the order of tens, at worst, hundreds of seconds to train the model. Here is a summary of the operating system just to show how this is used in the hospitals. So the electronic health record system provides the data. These data are then fed into the Medco database, and this leads to the encrypted data exit, and then it runs across those. We've deployed this in 3 hospitals in Switzerland, and making use of this for, let's say, an application case in oncology. And we are in ongoing discussions to extend this to additional hospitals in Switzerland. This shows how the interface would look like in oncology, comparing the efficacy of 2 drugs or 2 treatments more generally. Here, the number 1 and the number 2, or let's say the red and the blue. And as you can see, what is plotted here, the x-axis is the time after beginning of the treatment for the patients, and here the survival probability. And clearly, as you can see in this case, blue appears to be superior to red. So this is in oncology. In the case, now we have also recently started to work on applying this to COVID-19 data in an international consortium. You can see the location of the partners on this map, and you can find here the URL of the project. To recap, these are the features and guarantees that are required for such an endeavor. So what is needed in terms of functionalities are the descriptive statistics. One also needs set operations, cosine similarities are also very handy, linear regression, logistic regression, GLMs, and also machine learning, as we've seen. Data security. The data never leaves the data provider's premises. And very crucially, the intermediate computation results, or the intermediate aggregate results, are always encrypted. And what I've shown is actually based on lattice, so is also quantum resistant. Right? In terms of privacy, the idea is that the query only sees the final result. Let me conclude. So as we have seen, the current situation of multi-site data management is unsustainable and unacceptable. The solution, or at least part of the solution, consists in making use of appropriate cryptographic techniques that I've presented as multi-party homomorphic encryption, or MHE, that performs computations without seeing the data. And this is provided by homomorphic encryption and relies on decentralized trust. And this is what is brought by secure multi-party computation. There is no need anymore to transfer the data. And this is very crucial. There is no loss of control. And we believe this is going to be a very powerful incentive to make the absolutely needed progress in terms of homogeneity of the data and the willingness to collaborate in this field. So if we achieve this, we believe that such a systematic approach will streamline the approval processes by ethical committees. And this will also provide the needed mathematically proven data protection. Right? So dear colleagues, please join us in addressing the problem of securing health data sharing. The problem is absolutely crucial, is of strategic relevance, and is vastly under-researched. And I can tell you it's really fun. Thank you for your attention.